Prohibido comer en clase. Buen provecho.
No me mister, es un juguito nada más, mire, aquí está. No le enseño porque no me patrocinan, va.
Ok, ok. Cheque. Good morning, guys. Remember turning on your cameras. That way I can check your assistance. So please, for those students who have any trouble with the camera, advise me by the chat.
Sí, era mío, pero ahorita voy a clase.
Okay, there he is. So good morning to everybody. Praise be the Lord.
Now and forever.
Now forever. And we want to start this new topic related with trigonometry. Look, there are many topics interesting that helps you go more deeper to the mathematics skill you should win through all those years you have been studying mathematics, okay? Starting from 7th grade until the last semester, all those mathematics will be useful, okay? Because we want to conclude how to apply the logic of the mathematics in this kind of exercise. Okay, so in order to explain you how this topic is, we want to try some easy identities. Okay, we're going to start with this. But when we talk about identities, what do you think we are talking about? Just one or two opinions. Mathematical identities, of course. I want to see if you have like a clear idea about how this is. How this is. I mean, how is this? Sorry, how is this? Have you ever heard that word identity? Because say that they are equal is not too much. If you're thinking on it, saying that they are equal expressions is not too much, okay? Because identity goes more deeper. So here we have the objectives for this topic, because this topic will be very long. We will be with this like 5 weeks, okay? Because it's not too easy. But I want that you use all the algebra you have been knowing, because it's gonna be useful here in this trigonometry. So all the mathematics you have been using right now, and specifically the algebra, is gonna be useful here. So we wanna list the properties useful to prove trigonometric identities. I will give you like the list of the principal ones, and I suggest to you to screenshot this one and print it and have it over there, in a separate sheet of paper or in an index card. If you want to do it at hand and read it, no problem, it's better. And I think one homework will be related with that, okay? So then we want to use the algebra to simplify trigonometric expressions, trigonometric expressions. You will see how is that. And specifically here, the techniques like guess and check, the techniques of the difference of two squares, the techniques of the multiplication of polynomials, the multiplication of eras. I don't know if you remember that topic. In Spanish, it's called rise, I remember. But I said eras because that's the name in Spanish. And I think you remember not that so much because you make a joke with that one, okay? I call it rise. And I think you use that one to make the joke. Was Real Academia Española, but it's not like that. I mean, it's mathematics. So rise are related with rational algebraic expressions. And all the algorithms we use, like the algorithms to add different and same denominator, the algorithm to multiply, the algorithm to divide expressions, applying EAR operations, or the property it names is the division of complex fraction, will be useful in here. That's why use algebra to simplify trigonometric expressions will be useful in this type of exercises you will see right now. Those are not numerical exercises, okay? You don't expect a numerical answer for this kind of exercise, okay? So here you're gonna look for sentences, what we call in math sentences, in order to conclude one identity. Okay, other objective is simplify trigonometric expressions and in general. So then we will see other methods, not just the algebra, help us to simplify trigonometric expressions. You will see then that there are so many more methods. And we want to demonstrate the truth value of an identity. Can you tell me one of the truth values that you know? You know through two truth values. Which are these ones? Nobody knows? Probably you don't remember it, but I think you studied this in one class in symbolic logic. There are just two truth values.
True and false.
Yes, true and false. I mean, there's no, it's just yes or no, there's no maybe. For this mathematics, there's no maybe or probably, okay? Or possibly, no. There's no like that. There is just yes or no, is just a true or false kind of exercises. It's not about the, I mean, you will use many logic in here, okay? You will use many logic in here. And it's, to be honest, solve one exercise of this one is like complete, I forgot the word for rompecabezas. head breaker. No, don't know if it's like that. Can you remind me the word for rompecabezas?
Puzzle.
Sorry, a puzzle. Yes, will be like a puzzle, and you will construct the puzzle, not that you're going to have the pieces. The pieces will be given by the analysis of the exercise you do. Okay, and the other objective we're going to have is identify the fundamental technique to establish an identity. This is what we're going to do, establish identities. And if you see, this is on page 500 something, don't remember specific page, and you can start looking at it. I mean, there's no a lot of information of this, but we have to extend a lot from this because it's one of the most important topics of 11th grade. Because here you apply many techniques of mathematics you have been knowing during or passing all those years. So here we go, like with the basic idea of trigonometric identities. And when we talk about trigonometric identities, are equalities that involve trigonometric functions and are truth for every value of the occurring variables where both sides of the equality are defined. Two functions are identically if, okay, it's not two, it's two functions are identically if something like that happen. F of x equals g of x for every x which in both functions are defined. For example, you have here two expressions that looks different, but they are identical. And that's why in mathematics, this idea of the identities is very important. For example, if we choose an x value like 3, what's gonna be the answer here? You can get it in the calculator. What's gonna be the answer here? Forget this part right now, okay? Forget this part right now. We're gonna concentrate just in this one. Then you're gonna have 3 plus 1 to the second power. 3 plus 1 is 4, and 4 to the second power is exactly
16.
16. So we're gonna see now if this 16 it's equal to the other expression taking x times 3. So then you're gonna have 3 to the second power. I'm gonna help you with the calculator. Let me see if I'm showing you this. Yeah, there he is. So we're gonna have 3 to the second power plus 2 times 3 plus 1. If it gives me 16, means that they are identical. Okay. Means that they are identical if for every value that you choose, can be 3, can be 16, can be 20, can be any value that's happening, okay? If that's happening, means that they are totally identical. But you will not try with the numbers from 1 to 1 million just to look for one number that doesn't fit on this, no. And that's why algebra helps us a lot in here. This is an algebraic property. If you remember, at the end, this expression, this one I try to close to circle right now, is the same as you have x plus 1 times x plus 1. And the algebra helps us to multiply polynomials. And at the end, the product of this polynomial will give you exactly like that. So this what I did right now, this what I did, this situation that I did, solving this property is establish one identity. And essentially that's what we're going to do, but with exercises like this one, okay? Just to conclude it, I'm gonna show you how. For example, what means x plus 1 to the second power means x plus 1 times x plus 1. And you can solve that one. This is just x to the second power, then x times 1, which is 1x or just x. Then the same here, x times 1, which is 1x, and 1 times 1, which is 1. So then you have like terms, and here you conclude x to the second power plus 2x plus 1. So there he is. We already conclude an identity, and the way to do it was, in this case, using the algebra. And of course, that's the way we're going to do. I mean, then we will look, for example, a way to convert this expression into that one. And essentially, again, the answers we expect for this type of exercises are not numerical answers, okay? I'm not gonna expect a number like an answer. I'm gonna expect an expression like this one, like an answer. And for that reason, there are many trigonometric identities that already exist. And practically we're gonna base on that one in order to conclude the other ones. We're gonna try some exercises today, and that way you will see what is the thing I'm talking about. I mean, this topic is not too easy. That's why we're gonna give this like 5 weeks. It's not too easy, but I want that you have not the basic ideas. I want that you have the ideas in order to solve these kind of exercises, because just one exercise will take us, I don't know, probably the 30 minutes or the 35 minutes these classes are. So let's start, and here it is. And I'm gonna start with the basic trigonometric identities. You should screenshot all those identities, and we're gonna try to demonstrate or to prove some of them. I mean, when I say proof, is like we concluded with this, one right now with x plus 1 to the second power, okay? See how can you write this ones. We're gonna start with like the two basic ones with the quotient identities. And here you have tangent of one angle, it's equal to sine of one angle over cosine of one angle. Cotangent of one angle is cosine of one angle over sine of one angle. From where this come from, okay, explaining you from where each of these ones come from, it's not gonna be the topic, okay? We're gonna assume these ones, we're gonna take these ones like truth or like properties we're gonna use later. But just to tell you or to remind you a little bit, if you remember, the first trigonometry we studied was related with that unitary circle. And in the unitary circle, I remember that we conclude that tangent, it's equal to y over x. The tangent of any angle is equal to y over x. And if you remember, y is sine of x and x is cosine of x. And that's why at the end, this is just sine over cosine. But that's just like one idea to show you from where this comes from. Of course, from where this comes from, it's important because the origin of each of these identities will help us to conclude the important relationship they create. So I hope that you screenshot these ones because then they will be useful, okay? Or copy it, or I don't know, but I think this first class is like more theoretical than practical. These first classes today and tomorrow. And then we will start with simplifying trigonometric expressions. And then we will go with the proof or establish some identities. So here I have another properties or another identities. And in this case, we have other three that are very famous: cosecant, secant, and cotangent. These are called the reciprocal identities because they switch the position of the sine, cosine, and tangent. Okay, they create this kind of idea. They are not inverse function; they are reciprocal identities. Okay, so it's something different. You don't get confused with inverse function and reciprocal, because the idea is different in trigonometry. Okay, there you have cosecant of alpha is 1 over sine. It's something we already did too. And if you remember, that happens because sine, for example, sine of any angle was opposite over hypotenuse. And cosecant, which is the reciprocal, will be hypotenuse over opposite. So essentially it's like have this one, this expression over 1. 1 over opposite over hypotenuse, a big one, there he is switch upside down those expressions. How? Because you're gonna write 1 over 1 and then you're gonna apply your operation. So then you're gonna have on the top the hypotenuse and in the bottom the opposite. So essentially you're gonna have the switching upside down the position of that expression, which is sine. Okay, that's like the origin of this one too. So try to screenshot this and or copy these three reciprocal identities. Of course, these are not the only ones. Then we will conclude something about these three, the other ones. I mean, we conclude something about sine, cosine, and tangent. So here we go. And we're gonna make a short proof. For example, I want that we establish the identity of cotangent of alpha, which is equals to cosine over sine. And for that reason, we're gonna make this short proof in the whiteboard. That way you will see what's going to be or how it's going to be the work we're going to do. Again, it's not a numerical answer, okay? So here, if you see, there are all the properties, okay? Here, I'm gonna share this to you too, this picture. And that way you're gonna have like better control of this. So there's one property we cannot use. Okay, we're not gonna use all those properties right now because we didn't see it. We didn't study these ones. So don't worry about these properties. Then we will see what can we do with these ones. Something else we cannot use, we're not allowed to use the same property to conclude the property. So all that we can use are the quotient identities, except in this one, which is the one we're proving, and the reciprocal identities. So y cotangent of alpha, it's equal to cosine over sine. Everything or all these starts based on cotangent, okay? The only thing we know about cotangent, if you see here it is, I mean, there's no other cotangent in all those formulas, just in here, if you see it. If cannot see it, gonna zoom a little bit. There he is. Cotangent is 1 over tangent. So what we will do to prove this identity is that we're gonna choose that left side, cotangent of alpha, and we're gonna rewrite this expression. According with this property we have in here, cotangent of alpha is the same as you have 1 over tangent of alpha, or 1 over tangent of the angle, okay? In this case, I choose alpha, but can be any other angle, can be X, can be any other, okay? So here we go. We know that, but for that, I mean, we're too far away of conclude that this is going to be equal to cosine over sine. And that's what we want. We want to show that cotangent at the end becomes to be cosine over sine using the algebra and using all this bunch of trigonometric identities. I mean, not all of them, some of them, the ones that will be useful. And for example, the only thing that we can do right now, it's look for what means tangent. If you see, tangent means, I mean, there's no other one that works with tangent. I mean, it's that one. Tangent equals 1 over cotangent, but then you're gonna work with cotangent again, and you don't want that. You want to work with cosines and sine, like you have it in the exercise. But if you see here, there is one option that helps you to be closer to that. Tangent of alpha, it's equal to sine of alpha over cosine of alpha. So paying attention in what's going to happen right now. Now we want to change that expression. And instead of talk about tangent, now we want to talk about sine and cosine. So the one we already have in the top is going to be there. And tangent will be sine of alpha over cosine of alpha. And here the exercise is almost done. If you see, what I did is apply this property. Sine of alpha over cosine of alpha means tangent of alpha. So that's the idea of the identities. Being replacing that expression for something that is identical but doesn't look like. That's the idea of mathematics, right? Those expressions are identical. Yeah, they don't look like, I mean, this one and this expression, they don't look like, but they are identical. This is the magic of the mathematics too. I'm gonna continue the exercise here and we will do something. Here, I will apply something you really like and I'm gonna write this one like a fraction. Just to explain you something. When you have expression like that one, 1 over another fraction, and here you have the other fraction. What you have to do is try to apply this one, what you call the EAR operation, which normally is called like the complex fraction division, okay? So here we go, the extremes with the extremes and the middles with the middles. And that way we conclude next. We conclude 1 times cosine of alpha over 1 times sine of alpha. What happened with those products? 1 times cosine is cosine of alpha. 1 times sine of alpha is sine of alpha. And if you see, now we reach what we want. We want to convert this cotangent of alpha into cosine over sine. And essentially, this is what we did. We convert that cotangent, we start with cotangent of alpha, we convert into 1 over tangent, then we convert into 1 over sine over cosine, and then we convert that one into cosine over sine, which is what we want. So this, what I did right now, is the proof of one identity, is establish one identity, and it's the work we're going to be doing. It's not complicated. You must have always and every time all these properties, okay? All these identities. These will be useful every time. And for all the exercises we're gonna try, they always will be there, but you should have in your hands too at the moment to solve this type of exercises. Do you have any question about this first proof we did? It's an easy proof, to be honest. There are some more complicated, longer, that require more algebra. But all they work like this, like a puzzle, okay? You go like step by step in order to get the other, to see what happened if you change something, to see what happened if you apply your operation, to see what happened if you, and that's the way to do it. It's like a kind of trial and error. But if you use your logic, then you will not mistake, because at the end, for what is useful, the logic, okay, to make predictions, to make good analysis, and to take good decisions. And this type of exercise helps you to develop a lot of this. Okay, so do you have any question about that one? No question, I think it was clear. So there are some more properties. For example, it's possible to conclude that cosecant, if cosecant of alpha it's equal to 1 over sine, then sine is 1 over cosecant. That's like a little proof we're gonna do in the whiteboard too, but that one has an interesting trick. And normally in these exercises of mathematics, you can apply these, you're gonna apply these tricks. So we already make the first proof related with the cotangent. Now we're gonna do this weird one. That's so weird. I mean, we will not solve exercises like this one. This one is like to convert one identity into another one. So essentially what we wanna use is this identity, the whole identity, and we wanna convert it into this one. It's possible if we understand that this works like an equation, okay? But to be honest, these are not the type of exercises we will use. We will solve, I mean. So the Pythagorean properties are not studied, so we're not gonna use this one. Odd and even properties, yes, are not studied, so we're not gonna use this one. So we are allowed to use all these ones, okay? Of course, that's one too. That one is impossible, and that one is, this one is impossible to use because it's the one we wanna conclude. This one, look, it's already there. So I'm gonna explain you how can we conclude that, how can we convert that cosecant into sine, and how can we convert that 1 over sine into 1 over cosecant. It's a simple procedure, but in this case, it's not an identity. And I'm showing you this because what I'm doing is transforming the equation into an identity. This is another procedure, which is not the one we're gonna concentrate, but I'm saying because there are many exercises in the book that works like this, and we will not do it. So we're gonna concentrate just in identities, just in exercise like this one, where you start from one of the sides of the identity and conclude the other one. These ones are very different, okay? This one is, we're gonna use one equation to conclude another. So here it is. We start with cosecant of alpha, and that's gonna be equal to 1 over sine of alpha. I'm gonna conclude with this. Tomorrow we're gonna continue. And it's not easy at all, okay? It's not easy at all. It's easy when you have like clear what's gonna happen if you do something. Okay, what I'm going to do with this exercise is that I'm going to divide everything, and here comes like the tricky part. I'm going to divide everything by cosecant squared. And why I'm doing this? Because I want to look for the way to work with 1 over cosecant. And I think doing it like this, then we're gonna have this expression like we want it, like I told you. So we will see what to do in this exercise, and it's not complicated. So if I divide by cosecant squared, I have to divide by cosecant squared in the other side. So here I'm gonna divide, essentially is have the expression below. So it's gonna be multiplying this one below. cosecant squared of x. So what happened here? We will see what happened. What we want to do is like, for example, here you can simplify very quickly. Cosecant, one of the cosecant upstairs with the other cosecant below. I mean this, that's what I'm saying here, and this one. And now this part becomes to be 1 over cosecant of x. Not a square, not cosecant squared because you cancel one of those. This is like one idea. Because what we want is convert sine, we want to convert this into sine of alpha equal to 1 over cosecant. So I think that part of 1 over cosecant, it's already here. Now, how can we solve this other part? So for this other part comes like the tricky part. And the expression we have is 1 over sine of alpha times cosecant of x times cosecant of x. If you see, what I did is that I separate that cosecant square into cosecant times cosecant. So we already have the first part, which is in blue, 1 over cosecant of x, not of x, sorry, of alpha. And that's gonna be equal to, okay, here comes like the tricky part. And probably you will say, why are you doing all that? Okay, remember that now we have this part, of this equation, of this identity, we already have that part, the right part. It's on the left, no matter, then you just swap the expression. Now we wanna convert all that in just sine. It's possible? Yes, it's possible. I'm gonna show you how. We can convert those expressions, and here comes the tricky, into 1 over sine. Why we can use this one? Okay, because the property is here. It's that same property. So we can rewrite those expressions. And don't worry if you don't get it right now. Just showing you how it's going to be the work we probably will do later. And we want to write those expressions like 1 over sine of alpha times 1 over sine of alpha. And if you see what's going to happen below, there are some expressions that will be canceled. Here you have to write this 1 over 1. And the product of these expressions were like sine times 1 and 1 times sine. So then you can cancel everything here. The 1 with the 1, the sine with the sine, and at the end you just have 1 over sine. So here we go, and we almost conclude the exercise. Cosecant of alpha, which is equals to 1 over sine of alpha. If you remember here, I told you, you can write the 1 at the top here and apply what we call the year operation, which name is the complex fraction division, and conclude next. So here it's 1 over cosecant of alpha equals to 1 times sine of x is sine of x. And then 1 times 1, this expression below this one, it's 1. I think sine over 1 is the same of half sine. So at the end, 1 over cosecant of x, it's equal to sine of x. And we can swap this expression. I'm going to rewrite it here. We can swap those expressions, not x, sorry, it's alpha. And swapping those expressions, now we have what we want. And if you see, we finished. Sine of alpha, it's equal to 1 over cosecant of alpha. And that way we conclude what we want. Here it is. If cosecant of alpha it's equal to 1 over sine of alpha, then sine of alpha is 1 over cosecant. Yes, it's true. These are kind of exercises of prove the truth of one identity. Okay? If you start with one equation and conclude the other one, it's another way to establish identities, but not the way we're going to study, to be honest. It's a weird one, but if we conclude this one for, look, there's one for cosecant, there's one for secant, there's one for cotangent, we can immediately conclude the same for the rest, okay? And that works. So I hope that you start like looking the exercises, the pages. I don't remember right now what's the page of this, is 500 something. You should look on the book and start reading the information related with the identities. Okay, I already took 1 minute of your time, so thank you for your time, guys. I hope that you start analyzing those topics. And see you in the next one. Bye-bye. Have a nice break. and have a nice day too.